We have studied in part 1 of the video electric charge and electric forces. And now in the second part of the video, we'll define the electric field. Suppose we have a system with many charged particles. Let's say n is the number of charged particles. Then what is the force on one of the charges? Let's say on the charge Qi. I is an index that labels the different charges, so I runs from 1 to n. Now, we know from the part 1 of the video how to calculate the force on Q sub I. We apply Coulomb's law and superposition. The force on I is the sum for all of the other charges, K Qi Qj over Rij squared, R hat Ij. So we have many charges, but let's say one of them is the charge we're interested in. So that's the charge I. So that's Q sub I. And now someplace there's another charge, Q sub J. The force on Qi, due to the presence of Qj, let's say these are both of the same sign, will be in some direction. We call that K Qi Qj over Rij squared. Rij is the distance between Qi and Qj. Now, that's not the force, that's the magnitude of the force. The force has to have a direction, so we have to multiply that by the unit vector, r hat, pointing in the direction from j to I. So that's r hat ij. Now, if we have many charges, they will all create a force on Qi, and we have to add up all those forces. So this Greek letter sigma means sum. And Rij is the vector from Qj to Qi. Let's put that in a different color. So here is the vector R vector Ij. It's the vector from I to j. Now, the force is not action at a distance. There exists a force field. And E of x is the electric field. It's a force field. Actually, I have this wrong. This is xj minus xi is Rij. Xi plus Rij is xj. All right. However, the force is not action at a distance. There exists a force field. At every point in space, there's an electric field vector. So the electric field extends throughout a volume of space. At every point in the volume, there's a field vector, E of x. So in other words, the field, what we call the field, is a vector function of position. And then the force on a particle is the charge of the particle times the electric field. So that's the definition of the field. E is F divided by Q. What's F? F is the force on a charge, and Q is the value of that charge. I can think of Q as a little test probe. I put a little test particle at some point x. I measure its force, say by observing its acceleration. The force divided by the amount of charge of that test particle is the electric field at the position of the test particle. So that's the definition of the field. E at x is the force per unit charge on a test particle located at x. Now the electric field exists at x even if there's no test particle. Think of the test particle as a little probe. The electric field exists even if you're not probing it. So I guess I could say E of x is the force per unit charge if a test particle were put at x. Now this field is not just a mathematical theory. When the theory was first developed, it was sort of viewed that the field was kind of a mathematical description of the force. But as time went on, we became aware that the field is not just a mathematical quantity, not just a mathematical theory. The field is physically real. It's the field that exerts the electric force. The other charges don't exert the electric force because that would be action at a distance. The other charges create the electric field, and it's the electric field that exerts the force. Because the electric field is real. The electric field is just as real as the charged particles. So that's field theory. It was developed by the Scottish physicist James Clerk Maxwell, starting around 1860. And in fact, Maxwell developed a complete field theory for electricity and magnetism, and he showed that that field theory describes light and all other forms of electromagnetic radiation. Eventually, we'll see that the electric field has a form of energy, which we can call field energy. So it's real. It possesses energy. It exerts forces on charged particles. There's a way to visualize the electric field, which is to draw the electric field lines. Here's an example. Suppose we have a positive charge at this location and a negative charge at this location. If we put a test charge anywhere in this volume, well, this is only drawn in 2 dimensions, but you should think of it as a 3-dimensional field. If we put a little test charge at any point, let's say here, so there's a test charge. These are the sources for this black field. These are the sources. There's a red positively charged sphere and a blue negatively charged sphere. And they create an electric field throughout the volume of space. And if we put a little test charge at this point, it would experience a force directed tangent to the field lines. The field lines are curves which are everywhere tangent to the electric field. So if we put a test charge at this point, it'll experience a force in this direction. And that force is equal to the charge of the test particle, the charge of the probe, times the electric field at that point where I put the probe. E at x. Now I should remember, force is a vector. Charge is not a vector. So electric field has to be a vector, because it's the force divided by the charge. It's a vector divided by a scalar. It'll have a direction. It'll have the direction of the force. X I should also indicate as a vector, because the particle can be located at any point in this three-dimensional space. Now the electric field exists at this point, even if I don't put the probe there. The electric field doesn't depend on the probe. It doesn't depend on the test particle. It depends on the sources. Now, you can see from the picture, near a positive charge, the electric field direction is away from the charge. That's because if I put a test charge here, positive test charge, it would be accelerated away from that positive charge. Like charges repel. Think of the test particle as something very tiny with infinitesimal mass, for that matter, infinitesimal charge. It will experience a force directed away from the source. So the electric field lines point away from the source if you're near the source, so that the effect of the other source particle is small. Because remember, the force decreases as 1 over r squared. So if you're in the neighborhood of this positive charge, this negative charge will have a little bit of an effect, but very small. On the other hand, so near a positive charge, E points away from the charge. Near a negative charge, E points towards the charge. That's because if I put a little test charge here, positively charged, it'll experience an acceleration toward that negative source. Now, okay, so the electric field exists at every point in space. Near a positive charge, it points away from the charge. Near a negative charge, it points towards the charge. At other points, the field sort of curls around. It starts on a positive source and it ends on a negative source. So, you get this called a dipole field. It has two charges, dipoles. And, the field lines swing around, coming out of the positive charge and going into the negative charge. We sometimes call this a source, and this is a sink. So it's like a flow which flows out of the source and into the sink. Flow of what? Well, flow of electric influence. That's field theory. The electric force on a charge is exerted by the field at the position of the charge, not by the distant sources of the field. So if we put a charge at this point, it experiences a force. And the force is not due to action at a distance from these two particles. The force is due to the fact that there's an electric field at that point. And the electric field exerts a force on the charge that I put at that point. The definition of the electric field, we went over it before. If we put a test charge at position x, then the electric force is Q times E of x. Or in other words, E of x is equal to the force per unit charge that would act on a test particle located at x. So the force on Q is equal to the charge Q times the electric field. Now the electric field spreads out through the whole space, so the electric field at what point? Well, at the position of Q. Now, what's the unit for electric field? Well, you see, electric force is a force, so it's newtons. Electric charge is coulombs. So electric field has to be newtons divided by coulombs. So the unit of the electric field is newtons per coulomb. Later on in the next chapter, we'll define a different unit of electric field. There we'll see the electric field is the volts per meter. Volt per meter. But we don't give electric field a special name for its unit. We don't name Newton per coulomb some special name. Newton per coulomb is one way to write the electric unit, the electric field unit. Volts per meter is just another way to write the electric field unit. Now, where does the electric field come from? Well, it turns out there are several ways in which nature can create an electric field, but the simplest way, and what we'll be talking about in this chapter, is the electric field is produced by one or more charged particles. When the electric field is a constant in time, there must be a charge which is creating it. So that's called the electrostatic field. So let's consider just one source. Let's call it Q. It has a charge, some number of coulombs. Maybe Q is equal to, 1.5 coulombs. And it's located at some position x sub Q. Then what's the electric field at a different position, x? So here's the picture. We have a source here. And let me put its position in purple. So that's the position x sub Q. That's the position of the source. And now I want to know, put it in a different color, I want to know what's the electric field at this position, some position x. Well, I defined the electric field as the force per unit charge on a test particle at x. So let me imagine laying down a little test particle at this point. I can think of that as a little infinitesimal particle with an infinitesimal amount of charge. So the electric field is really just the electric field produced by this macroscopic source. And I want to know what's the electric field at this point. Well, I put my little probe there. I put a test charge there. I measure the force on it with a force meter, or I observe its acceleration or something. Then the electric field at that point is the force divided by the charge. In other words, 1 over Q times the force on this test particle. Now I'm interested in the field created by this source, so I just want the force in the presence of this source. But I already know that. That's Coulomb's law. The force on the test particle is KQQ over r squared times r hat. So this is the force due to the presence of the source charge, capital Q. It's KQQ r hat over r squared. Magnitude is KQQ over r squared. The direction is r hat. R hat means the direction away from the source. R is the vector which goes from the source to the point x. So r is x minus xq. It's the vector from the source. So let me draw r here. Here's r. Well, I didn't draw it very well. Here's r. R is the vector from the source to the point x. So r is this vector. That's the vector r. What happened? R is that vector. That's the vector r. Its magnitude is the distance from the source to the test charge. Its direction is directed from the source to the test charge. It's x minus xq. You know, if I set up some coordinate system where this is the origin, then xq would be this vector, x would be this vector, and x minus xq would be this vector. Or xq plus r is the position x. Now look what happens. The charge of the test particle cancels. Little q cancels out. So the electric field due to a source charge q is kq over r squared, r hat. Or r hat is the direction away from the source particle. So here's an equation you've got to have in your notebook. You'll be using that over and over again. Force is kqq over r squared, r hat. Electric field is kq r hat over r squared. Because the second charge, which comes into the force equation, cancels out when I divide through by the charge. Again, K sub c is Coulomb's constant. That's 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Now that's the electric field created by one source particle. What if I have many particles, many charged particles? Well, then the electric field at x will just be the superposition of kq over r squared times r hat, where all of the source particles are added together, or the fields created by all of the source particles are added together. So let's suppose the source particles are located at x1, x2, x3, x4, x5, and so on, xj. Suppose there are n source particles. So what's the field produced by n charged particles? I have to sum j equals 1 to n, kq over r squared r hat, for each of those n source points, or source particles. That will then give me the electric field at the point x. So again, that's how this figure was created. You assume there's a positive charge q at this point, a negative charge q at this point. Suppose you want to know the electric field at this point. here. Suppose I want to know the electric field at this point. Well, I have a contribution from this source, which will be more or less in this direction. I have a contribution from this source, which will be more or less in this direction. This will be actually fairly small because it's far away from the positive source. This will be larger because it's close to the negative source. So the combination, or the vector sum, will be the direction of the electric field at that point, xq. And so on. I can figure out those electric fields at all points throughout the volume, and then I can connect the vectors by curves such that everywhere the curve is tangent to the electric field at that point. Now there's a section in the book called charged particles in an electric field, E of x. Need this picture again, but let me draw it over again. So one of the sections in the chapter 15 is called charged particles in an electric field. So we have these two particles that create an electric field. Now suppose I put another charged particle, like here. What's the effect on this charged particle? Well, it experiences a force tangent to the field lines. Let's put it up here. Let's draw the force sort of in this direction. So if you know the electric field, you don't use Coulomb's law. If you already know the electric field, you don't use Coulomb's law. To determine the force on a charge, you just multiply the charge times the electric field. Now, in the textbook, there'll be formulas for other kinds of electric fields. This is the electric field for point charges. Another example would be the electric field in a capacitor. You have two charged metal plates. So suppose I have two metal plates, put them in different colors. I've been using blue and red, so let's make this one blue. And now let's make this one red. So you have a positive plate, a little positive flat plate. And here I'd have a negative flat plate. Let's put that one in blue. Oops, I wanted that one in red. I want this one in blue. So I have a little flat plate here, colored blue. That's called a parallel plate capacitor. One side is positively charged, the other side is negatively charged. There'll be an electric field. Put the electric field in black. The electric field will point from here to here. The electric field will be mainly concentrated in the region between the two plates. There'll be an electric field between the plates, and the electric field strength will be the charge density divided by epsilon 0. So you see, I wouldn't use Coulomb's law for that. I would use the electric field due to parallel plates. That's a formula you can find in the chapter. Or maybe in chapter 16. I'm not sure. All right, well, that completes part 2 of the introduction to chapter 15. So if you've watched part 1 and part 2 of the introduction to chapter 15, now you should go and read chapter 15. And then you can do the homework problems.